in Germany.
Thank you. Thank you, Antonio, for the kind introduction, and quite impressive being able to remember these dates. Also, thank you to Gonzalo, Geert, and Elvin for the kind invitation and for putting this workshop together. It's my first time at GSP, but I've been enjoying it quite a bit, so I will try to be back whenever I get a chance. So my talk is about a link essentially between graph signal processing and optimization, and the maybe slightly ambitious title is that to go beyond what I'll call consensus-based methods in decentralized learning, we essentially need to combine tools from both graph signal processing and optimization. And some very interesting things happen once we get there. Okay, so I think you have seen many slides of this kind at this workshop so far. What I will say is, maybe to complement what others have said before, is that it's clear that we're having an increasing amount of networked data generated across various devices, ranging from sensor networks, autonomous vehicles, social networks, power grids, mobile devices, or swarms of drones. And of course, GSP and graph neural networks are all about processing this kind of network data, right? And essentially extracting information about the graph from the data, or using information that we have about the underlying graph to say something about the data. When we're talking about distributed learning or distributed optimization, a lot of times we take a slightly different view at the problem, which is to say that there is some underlying graph topology that is going to limit interactions amongst agents, okay? So rather than thinking of this as a prior, we're thinking of this as a restriction on the flow of information, right? So in a sensor network, for example, you might have power constraints that limit the range of any given interaction. Autonomous vehicles may or may not be able to communicate with one another. In a social network, of course, there is links that determine who you're interacting with. Power grids naturally are a network as well. And in the case of mobile devices and drone swarms, we can make similar kinds of analogies. So to just outline the structure of my talk, so I will actually start by talking about consensus optimization, which we can think of as, let's say, a baseline approach to designing these intelligent distributed systems. And I'm quite aware that a lot of the seminal works on consensus optimization have been done by members of this community, okay? So for some, this will be quite a familiar topic, but I can also imagine that some people who might be interested in GSP, but not necessarily distributed learning, might benefit from kind of a more, let's say, broad introduction to distributed learning, okay? So I'll talk a little bit about different kinds of motivation and algorithms that we have in that setting, and also about performance trade-offs, because that's going to essentially set the scene for then going beyond, okay? And then we will motivate why there are situations where solving consensus optimization problems isn't necessarily the right thing to do in a networked system. And then I will essentially present 3 case studies, which are a collection of works where I will try to demonstrate to you that essentially a lot of the considerations that you're making in that setting, once you go beyond consensus-based optimization, essentially boil down to concepts that you will be very familiar with if you have any sort of exposure to graph signal processing and GSP, okay? So this, of course, all of what I'm going to be talking about today is a collection of joint works. So this includes Shrula Nassif and Cedric Richard at the University Côte d'Azur, Ali Said at EPFL, and then my current PhD student, whose name is Aaron Feynman at Imperial, and Shutian Wang, who is a former master's student who has unfortunately moved on to industry. Okay, so I will start maybe with the takeaway just to give you some context, okay, which is that when you compare graph signal processing and distributed learning, a lot of times there's essentially a very different way in which we can think about the graph, okay? When you're working with graph signals, when you're doing GNNs, you have an underlying graph which encodes a prior, which to you is information that you want to exploit, right? Whereas when you develop decentralized algorithms, your information is flowing over a graph, but it acts on you as a constraint. And if you wish, you would just connect everyone to everyone else, okay? And you would allow for a fully free flow of information, okay? So there's essentially a contrast in the way we think about graphs in these two settings. And my kind of claim throughout essentially is going to be that it makes sense to exploit graph structure and this prior information also in distributed learning, okay? And that's what I mean by going beyond consensus-based methods. Okay, so let's set up the problem. So our ultimate objective will be to learn, right? To build intelligent systems. And you can have different definitions of what it means to be intelligent or to learn. For me, for the purposes of this talk, I will ask my agents to build models, okay, that relate data in some way that's going to then allow them to make predictions or drive their behavior and so on, okay? So to this end, we're going to have each agent be provided with local data, okay? So that's X sub K and N. So K denotes the agent and N is going to throughout denote the sample. And then each individual agent is going to wish to construct some sort of a parameter W, and we're going to measure the fit of that parameter through some loss function Q, okay? And we allow the loss function as well to be local, okay? So then Q of W and X is going to tell me how well the parameterization W fits to the data X. Okay, and then I can formulate an empirical risk minimization problem by just collecting a whole batch of data and then averaging over my data. And that's one of the most fundamental ways in which we can learn, right? Okay, so let's go through, do two examples just to illustrate this. So we will do one that is more classical, which is least squares, right? So if I think of my X data as containing a feature H and a label gamma, then I can look for a linear model that relates H and gamma through W, right? So W transpose H is going to be an estimate of gamma, and then I can penalize any sort of deviation in the squared sense, and that gives me least squares, okay? So this is a very nice problem. It's quadratic, it's very well defined. We have very good algorithms and understand the fundamental limits of these kinds of systems very well, okay? But these days, of course, we're interested in things like deep neural networks, where fundamentally the problem is actually quite similar. So we again have an X, which contains a feature and a label a lot of times, at least in supervised deep learning. But then we're going to relate H and gamma in this kind of more complicated way, in this nested way, which in this case is a fully connected neural network, but of course it can be any sort of other architecture that you like, okay? And the point is both of these kinds of considerations give rise to loss functions of the form Q of W and X. And now, depending on your interests, you might be more interested in the non-convex setting or in the quadratic setting. But ultimately, for the purposes of this talk, a lot of times it won't really matter because we will just be talking about cost functions and gradient descent and so on. Okay, but certainly an active area of research has been to understand optimization algorithms in these more kind of complex landscapes, right? So we know, for example, that the LMS algorithm converges. What can we say about stochastic gradient descent applied to neural networks? Okay, but I won't be going too much into that. Okay, so then we've defined essentially an objective for every agent locally, and then the question becomes, so how are we going to allow our agents to communicate with one another? And there's different names that people use for different kinds of structures, and so I just have this slide here to essentially agree, hopefully, on some sort of a taxonomy for the purposes of this talk. So if you think of each agent as being represented by a node here on the slide, then we can label them 1 through K, and if there's no interactions between any agents, that's going to be an empty graph, right? And then there is centralized or parallel structures where you have a fusion center, and then each agent kind of iteratively can perform some sort of local update and then exchange with the fusion center, and you iterate this process. In the last couple of years, people have become very excited about this concept of federated learning, which is essentially just centralized learning with a number of asynchronies added in, with local updates maybe, and so on, right? But fundamentally, both of these approaches employ some sort of a fusion center that aggregates all of the data and acts as your orchestrator. And then on the right-hand side, we have a networked or decentralized approach, okay, where we throw away the fusion center and we just rely on peer-to-peer interaction. So now there will be no longer any one kind of boss or any sort of parameter server that's going to ensure that we are all synchronized on a model. Instead, we're going to all maintain our local models. And the kind of the objective or the goal in these decentralized structures is to then still be able to say that we're kind of behaving optimally in some sense, okay? So, and the key is, and a lot of what this talk is going to be about, the exact definition of what it means to be optimal in a multi-agent setting, okay? Now, the algorithms that I'll describe today will be decentralized, okay? So that means we throw away the fusion center, and traditionally, the kinds of justifications you will read in papers about why we should not rely on a fusion center, why we should do things in a decentralized way, it boils down to essentially constraints on the communication, right? So for example, it might be very costly for us to all communicate with a single parameter server. It might not be feasible for us to send a whole lot of data or a whole lot of parameter to some central cloud. Or considerations about robustness. So if you think of having a fusion center where an individual link may fail, if that link fails, then the node is completely disconnected from the network as a whole, and so you lose essentially your intelligence, right? Or, of course, if the fusion center breaks down, then the whole system breaks down. So these are the kind of classical reasons why we tend to employ these decentralized systems. Okay, but at the same time, you will find when you read a paper on decentralized optimization or learning, a lot of times we wish that we could do things in a centralized way. Okay, so we wish, in a sense, that we were able to aggregate data centrally and then do the processing centrally, because that essentially ends up serving as a sort of lower bound. Okay, and a lot of the analysis in consensus optimization, at least, goes down to trying to match the centralized benchmark. Okay, so how close can we get to a perfect solution where there is no bandwidth constraints, no considerations of robustness, and so on. Okay. And so this kind of goes, to this observation that I made earlier, which is that kind of throughout most decentralized kind of works, you will find this desire to avoid dependence on the graph topology. Okay, but we know, of course, from kind of results and insights, in GSP, that the graph a lot of times can contain some kind of quite interesting information. Okay, so the question is, how do we reconcile the two? Okay, then how do we now define globally optimal behavior, right, for a collection of agents? Of course, if we can define optimality locally by just defining some locally optimal model WK naught as the minimizer of the local risk function, J sub k, which is just essentially fitting the model to the locally available data. Or what you can do is you can pool the data. We're not going to do this in reality, but just for defining our optimization problem, we can pool the data to define a globally optimal model. And now this will be W naught. And this is the minimizer of a new function, J, where J is the average of the local objectives, okay? And the key is that if you look at the structure of J sub k, because it is the average over the local data at agent k, what you have globally is an average over the data across all, right, across all samples and across all agents, okay? So in some sense, this has a maximum likelihood interpretation. Okay, so you can make this a bit more precise. So if you suppose that your data locally, so xkn are independent observations of some random variable xk that follows some distribution that is parameterized by this vector wk star, if you then define your q's to be the negative log likelihood, well then the local maximum likelihood estimate is exactly the minimizer of this local risk function, okay? Now, if you assume that your data is spatially independent, and that the true parameterization is common, so wk star is equal to w star, then the maximum likelihood estimate of w star given kind of the collection of data across all agents is exactly this consensus optimization problem that we formulated, okay? And this is an observation that was, that's been made quite a while ago. And so this is one of the justifications for why we're interested in solving these consensus optimization problems, right? So we can essentially say that if we were able to solve this consensus optimization problem, and if the underlying data distributions are homogeneous, then this is optimal in some sense, okay? But the key kind of what I've marked as red here is that the underlying assumption to justify this maximum likelihood interpretation is that the parameterization is common across agents, okay? So if you're observing, for example, if you're considering, let's say, a sensor network where each individual agent is observing a single object or a single parameter, then this kind of a formulation makes sense, right? And then agents will be able to pool their local observations to generate better estimates of whatever parameter vector you're observing. But as soon as you deviate from this assumption of homogeneous data, then the maximum likelihood interpretation breaks down, okay? So this is, let's say a bit of a preview of where I want to go with this ultimately. Okay, so then, but let's assume for now that this consensus optimization problem is a meaningful problem to solve, okay? So then the question becomes, how do you develop decentralized algorithms for this kind of a consensus optimization? And there's different ways of deriving these algorithms, but I will just present one approach which I find to be quite elegant. And it works by first recognizing that if I evaluate all objectives at a common W, then this is a global problem that I cannot really decentralize, that I cannot really distribute. Okay, so what we can do is instead of evaluating J sub k at W, at a common W, we can evaluate it at local models, WK, but then essentially imply or require that there is local equality over neighborhoods, okay? So we will require that WK is equal to WL for all L in the neighborhood of K. And if you have now a connected graph, then this kind of an equality constraint essentially gives you global equality, okay? So we haven't really done anything except reformulate this in terms of an equivalent optimization problem. But now the key point is that most of the decentralized optimization algorithms that you will find in the literature today can be justified by, in one form or another, solving 10, okay? And I've tried my best to collect a couple of references here, which are, let's say, representative. And my goal is to give you a little bit of an overview of how you would now, given these very many different algorithms, how you could classify them or how you could think about them, okay? So kind of a broad overarching distinction that I want to make is between penalty-based algorithms, okay? So these are things like distributed gradient descent, and the first version of this you can actually find in the 80s by Tsitsiklis and Pertsekas. And then things like consensus plus innovations, okay? And then on the other hand, we have primal dual or gradient tracking algorithms, which are exact algorithms, okay? So penalty-based algorithms will reformulate this consensus constraint into a penalty and then solve an unconstrained problem, which is, of course, just an approximation, okay? Whereas algorithms based on primal dual algorithms and gradient tracking are able to solve the underlying consensus problem exactly, okay? So if the consensus problem is what you're interested in, there's certain advantages to using to using primal dual or gradient tracking-based algorithms. Okay, and then kind of another broad distinction that you can make is between the classical algorithms and their adapted and combine or incremental variants. Okay, so for example, the diffusion algorithm, you can think of it as the counterpart of distributed gradient descent, where you're doing something incrementally. Okay, so most of the algorithms that you find in the literature today, at least for first order optimization, you can interpret them as kind of falling into one of these categories. Okay, so I will not, of course, don't have time to go into the detailed kind of derivations of all of this, but I just want to illustrate a derivation of this class of penalty-based algorithms, which is going to be useful when we then think about how we can move beyond consensus, okay, or how we can interpret some of the things that we observe. So remember that earlier, we required WK and WL to be equal for every pair of connected nodes, right? So instead of enforcing this as an exact equality constraint, I can define some weights, CLK, okay, between any connected pair of nodes, and then penalize the deviation from consensus. Okay, so crucially, we're going to require CLK to be equal to 0 whenever L is not in the neighborhood of K. And you can imagine that as you now let eta go to infinity, this will give you, recover the consensus problem, right? But of course, for any finite eta, you will be solving only an approximation of the consensus problem. Okay. Another interesting kind of special case, which is not obvious at first, but once you think about it, makes sense, is that you also don't have a bias whenever the local minimizers coincide. Okay. So, and that's because if you have a point wk naught that minimizes jk for all k, right, then all of the gradients there will be the same, they will be equal to 0, and then this term will be equal to 0 as well. Okay. So crucially, whenever you have a very homogeneous problem, you don't introduce much of a bias, okay? And that explains why these types of algorithms can be quite effective, actually, when you have, for example, a network of agents tracking a common objective. Okay, so then to get to an algorithm from this optimization problem, it will be quite useful to define some more compact notation, let's say. So if you think about it, these WKs, they're describing the state of the network across the entire network, across the entire set of agents. And so it will be convenient to kind of summarize them into a single vector. So we're going to collect each of these individual weights into a common W, into a single W, and we call it calligraphic W. And you obtain it by just stacking all of the individual weights. Okay, and then the sum of the local objectives, we define this as calligraphic J of W. Okay, so just some notation. But ultimately, this allows us to write this penalized problem in a very efficient way. Okay, so using the Laplacian of the adjacency matrix defined by C, 15 is simply a very kind of compact representation of this penalized optimization problem. Okay, and now once you make that observation, now nothing is stopping you from applying gradient descent. And so if you do this, you end up with a very simple recursion. Okay, either in terms of W, right, this calligraphic W, or in terms of your local quantities. Okay, so what you end up with is a recursion that relates the local models to each other, right? And so how should your algorithm evolve? Okay, and this has a very simple interpretation. And in fact, the algorithm wasn't necessarily derived in this way originally, but the idea is that each individual agent maintains a local model. You perform consensus averaging over your local models, but then each individual agent is going to kind of pursue their own local gradients, okay? And so this is an appealing algorithm because it is quite simple, right? It is easy to implement and so on, but it is useful to keep in mind that we're not actually solving the exact consensus problem, we're only solving an approximation of it, okay? So instead of applying gradient descent directly to this quadratic regularized optimization problem, you can do things incrementally. So I can first descend along the negative direction of the gradient and then combine. Okay, so after I have descended, I can combine my iterates. And this gives you another algorithm which is called diffusion. Okay, so both fundamentally solve this approximate consensus optimization problem, but do it in slightly different ways. Okay, so then as a visual representation of what this then looks like, you have distributed gradient descent on the left, where agents are able to communicate while updating their local models, right? Because what they're communicating is W, and then they are just updating along and then kind of add the two effects, right? So you add the averaging effect and you add the mixing effect. So you add the averaging effect and you add the gradient effect. And then diffusion, on the other hand, is a sequential algorithm where you first update and then you average. Okay. So I will not show the derivations for the other algorithms, but I will just say that you can solve the exact consensus optimization problem via the augmented Lagrangian. Okay, and so this is something that has been done since around 2008, but there's a lot of details in how you exactly solve the augmented Lagrangian, and this gives rise to a number of different types of algorithms. And so an example of this is, for example, exact diffusion, where I've kind of marked in red what is different compared to your, let's say, classical penalty-based algorithms. So if you look at equation 20 and equation 22, this looks just like the diffusion algorithm. But what you have kind of in between is essentially a correction step that's going to remove the bias and ensure that you're solving the consensus problem exactly. And then there's another kind of class of algorithms, and I'm showing just one here as a representative example, which are these gradient tracking algorithms, where, again, the first two lines look very similar to the diffusion algorithm, but you're not descending along the actual local gradient, you're descending along an estimate of the global gradient, which you essentially compute using a sort of dynamic consensus scheme. Okay. So these are all these different algorithms. We have kind of this vague idea that kind of in the back of our mind, we know that some of these algorithms come from a penalized problem, which is an approximation, and some come from an exact formulation, either via augmented Lagrangians or via gradient tracking. Okay, but then the question becomes, so what's the performance of this kind of a scheme? Okay, so when deriving these algorithms, it's useful to work with exact gradients, but in practice, we're learning from either a large batch of data or we're learning from streaming data. And in these cases, we don't really have access to the exact gradients. We just have access to approximations of the gradients. Okay, so we're going to denote this by using this hat notation. Okay, so gradient hat or nabla hat of jk at w I minus 1 is going to be the estimate that we construct using just the instantaneous approximation of the loss through q, and then a realization or sample that we picked at time I. Okay, and so any of the algorithms that I showed, you can get stochastic versions of them by just replacing the true gradient by approximate gradients. And the kind of the key insight or the intuition is that because now you're using a stochastic approximation of the gradient here, what you're essentially doing is you're adding noise to your system, right? So I should be descending along the gradient of j. I'm instead descending along the gradient approximation, right? So the noise that I add into my system is given by s, which is given by the difference between the gradient approximation and the true gradient. Okay, and generally speaking, the performance of your algorithm will depend on how good this approximation is. Okay, so what do I mean now by performance of the algorithm? So you can study these kinds of systems now for a variety of different settings. And kind of one of the things people have done over the last 5 to 10 years is considered kind of increasingly general optimization problems, right? From convex to non-convex to the kinds of structures you get in neural nets and so on. But just to kind of get a point across, I'm showing you here what the performance trade-offs look like when you have a strongly convex and smooth objective, okay? So generally, your performance will depend on several factors, okay? So there is a certain kind of underlying, essentially information theoretic kind of limit on how close you can get to the optimal solution, okay? And that means that even if I had all of the data available at a central location, I wouldn't be able to do better than that, okay? And so that's this mu sigma squared over k here, okay? So you can see that performance depends on your step size. It depends on the quality of your gradient approximation. So sigma squared is the variance of the noise that you introduce, and then the number of agents, k, okay? And the scaling by k is what people refer to as linear gain, okay? And what that tells you is that as the size of the network grows, your performance improves. And that is essentially the reason, or kind of the carrot that we have, that we can essentially offer to any particular agent that will encourage them to participate in this kind of a distributed learning scheme, okay? So in addition to that, you have certain other factors that are essentially going to be the price you pay by solving this problem in a decentralized way. Okay, so in blue, you will find terms here that essentially look very similar for these different kinds of algorithms. Okay, so this is, you can think of this as the cost of decentralization. And this again depends on the step size, but now mu squared. Again, depends on the quality of your gradient approximations, but then importantly also depends on the mixing rate of your graph. Okay, so the idea here is that if you have a very densely connected graph where information can flow quite freely, you're going to get pretty good performance, okay? Whereas as your graph becomes sparser and sparser, lambda will approach 1, and then you're dividing by something which is close to 0, and kind of the cost of decentralization grows. Okay, and so this is something that is again common to these algorithms. But then what you have on the right-hand side here is the price that you pay by solving a penalized problem, right, instead of the original problem. Because remember, when we argued, or when we derived things like the diffusion algorithm, which is a penalty-based algorithm, we accepted the fact that we're not solving the original consensus optimization problem, and so that's the bias that you introduce, okay? And you can see again that this depends on the kind of the connectivity of your network, but then also the heterogeneity of your system, okay? So this is the local gradient of j sub k at the common minimizer, okay? At w naught. And this will essentially measure how heterogeneous your system is. Okay. And so again, kind of I want to stress this point, which is that we would like to just recover these green terms, okay? So if we could, we would end up with a more and more densely connected graph, right? Which will make lambda approach 0. And then all of these other terms, right, they will disappear, okay? So a decentralized algorithm for solving consensus optimization will always perform better the more densely connected your graph is, okay? Which is different from the way we think about graph signals, right, more generally in GSP. So just some kind of illustrations of these phenomena. So we can illustrate linear gain by considering a network of agents and then increasing the size of the network, okay? And if our predictions are accurate, then we should essentially, if we increase the number of agents by 10, we should see a 10-fold reduction in whatever kind of performance metric you're interested in. So that's what we're showing on the left-hand side here. Another way to think about this is to say that the network of agents will perform as well as one agent that has 10 times or k times the data. So that's what we're showing on the right-hand side here. Okay. And then just to illustrate this point about dense graphs, so if you have a very dense graph, right? So if I'm able to, in this case, I've generated an Erdős-Rényi graph where the link probability is 50%. So you end up with essentially a very, very dense collection of agents. Then there isn't really much of a difference in performance between the different algorithms. And in fact, all of these are going to match your centralized baseline. Okay, whereas as your graph grows sparser, you're going to lose performance for all algorithms kind of across the board, but your penalty-based algorithms are going to suffer more. Okay, so this concludes essentially my kind of quick recap of consensus optimization. Okay, fundamentally, right, the underlying idea is that if we have data that is homogeneous across the network, if we have IID data, then solving the consensus optimization problem corresponds to a maximum likelihood solution. And in that case, I can write down different algorithms that will do kind of have varying quality, but always measured against this consensus problem. Okay, so kind of to recap this, so far we were always talking about the consensus problem, right? And solving this kind of an average optimization problem makes sense essentially in two settings, okay? First of all, if your data arises from a common parameterization, right? So if it's either IID or whatever target you're trying to track is common, even if your data is not IID. Okay, so that's one setting. The other setting is if you're explicitly seeking a single model that fits all of the data. Okay, so you can imagine, you know, in a, let's say, machine learning setting, you might have data that is kind of dispersed across a network. The data might not be homogeneous, but you're looking for a single model that fits the data across the board. Okay. But if you think about, you know, let's say a decentralized multi-agent system, really, what's happening is I'm an agent with limited computational capabilities and limited data, and I have some sort of a local objective, but I'm trying to benefit from what everyone else knows. Okay. So how much I'm going to benefit in some sense is going to depend on the relationship between my objectives and my neighbor's objectives, right? And so we're going to explore kind of this consideration. We're going to try to make it a bit more precise in what follows. Okay, so this is the first consensus, the first case study, let's say. Okay, so our setting will be that agents are heterogeneous and they're self-interested, and they aim to estimate their local performance, but they're doing this using finite data, using stochastic gradients, right? So they're not able to do this exactly, and so potentially they could benefit from one another, provided that, you know, you collaborate in the right way. And the question is, how should you collaborate now if the data is no longer IID? Okay, because the traditional consensus-based kind of maximum likelihood interpretation breaks down. So just to motivate the setting, okay, we're going to start with a real data example. So let's say we're trying to do weather forecasting, okay? So we have weather data from stations across the United States, where we can collect in a feature age today's information about things like, let's say, humidity or temperature, and then the label gamma is going to represent whether it will rain tomorrow or not, okay? And so because this is a binary classification problem, it doesn't really make sense to do least squares, but we can instead do logistic regression. Okay, so this gives us the logistic regression loss. And then we can, you know, we don't have a graph explicitly given, but we can construct an adjacency matrix based on, for example, the Euclidean distance, you know, or geodesical distance between nodes, okay? And so what we will show is, so what we will study is now this penalized optimization problem, okay, where we're not enforcing exact consensus, but instead we're allowing for slack, okay? And we will plot now, or we will examine the performance of the resulting predictors for various choices of eta, okay? So what you can then see is, if you have a very small eta, this corresponds to very weak coupling between each individual model. And so that means that agents will not benefit at all from anyone's data in the network, okay? So this is essentially a fully non-cooperative approach to solving this problem, okay? So we end up with an approximation error, which is, or a prediction error around 30%, okay? Kind of on the other end of the spectrum, when you choose a very large eta, you're essentially enforcing the models to be common across the network. But you can see that actually in this particular example, the optimal choice of eta is somewhere in between, okay? So the right thing to do is not to enforce consensus of models. The right thing to do is to encourage somehow smoothness of the models across the network, okay? And this goes down to this, you know, the observation is essentially the conjecture that you can then set up is that, well, the way weather kind of behaves and the way you should predict the weather is not uniform across the whole of the United States, right? You have mountainous regions, you have regions next to the coast, and so what makes a good predictor for tomorrow's weather might vary spatially, but maybe locally, right, within a localized region, there is some relationship, okay? So you do benefit from some collaboration, but you do not want to enforce exact consensus, okay? So this is quite an intuitive way of thinking about things, but can we make this a little bit more precise? And now I will start introducing concepts which, to someone working in GSP, are not particularly new necessarily, but maybe you know, you will find it interesting that they can be applied to this optimization setting, okay? So when we're thinking about modeling spatially distributed data, quite a natural statistical model for this is the Gaussian Markov random field, okay? Where we're going to essentially impose a prior on W, so these are the local models, which follows more or less a Gaussian distribution, where the scale parameter is given by W transpose the Laplacian in W, okay? So by this measure of variability that you construct using your Laplacian. And there's kind of some details here which essentially boil down to the fact that the Laplacian generally does not have full rank, so you can't really think about its determinant, but you can still define this kind of a pseudo distribution. And then what we're saying here, right, is the scale parameter, it measures the variation of kind of the signal across space. And now if you plot realizations of this process for different choices of your eta, what you can see is that by choosing a very small eta, you're not really constraining your signals to be kind of common across space. Whereas as you increase eta, it's going to penalize increasingly deviations locally, and you end up with an increasingly smooth signal, right? From a small eta to a very large eta. Okay, so then we can now formulate, let's say, the maximum a posteriori estimate of the models for a given Gaussian Markov random field prior. And what you will find is that this actually comes back to the penalized consensus optimization problem, okay? So if we impose the prior of the Gauss Markov random field, that's going to give us this quadratic regularization here, whereas kind of in the first term, we have the local objectives, okay? So this is another way of deriving this penalty based formulation, right? So previously, we used this as an approximation for the exact consensus problem, whereas now we can interpret this as a different kind of problem, right? It is the maximum a posteriori problem for this very particular prior given by the Gauss Markov random field. And now this eta becomes essentially a tuning parameter that you can vary that's going to, well, A, vary the strength of your prior, right? So how much do you trust your prior information? How much do you trust the information that is contained in the local objectives? Or B, how smooth do you think your signal is, right, across space? And smoothness here, importantly, is measured along the graph, right, which is something that you're given as a prior, okay? So now, depending on your background, right, there's now two ways of thinking about this. Okay, so we've introduced essentially a hyperparameter, right? So if I don't know anything about my data, if I don't know anything about the prior or the algorithm, if I don't know anything about the data, the prior, or the algorithm, well then, you know, I can split my training data, let's say, into a validation set and a test set. and then I tune eta on the validation set and I test and so on. So this is one way of thinking about this. But I think, as signal processing people, we're not generally happy with these kinds of answers, right? So the question is, what is the optimal choice of eta, for example? Can you learn it from the data? And then how does the choice of eta and any sort of misspecification that you maybe have in your graph affect how well you're able to learn, okay? So as we'll see, it essentially boils down to some very fundamental GSP concepts. Okay, so just some observations, right? So as eta goes to 0, you lose coupling, okay? So you kill your prior and you essentially recover the non-cooperative learning problem. As eta approaches infinity, we are back at the consensus optimization problem. And so in between, you're going to end up somewhere in between, okay? So then the fundamental question is, for different choices of eta, what kind of performance can I expect? And how will that be affected by things like the gradient noise, the relationship between your underlying tasks, and the graph topology? Okay, so the way we can answer this kind of a question is by interpreting a decentralized learning algorithm as something like a graph filter. Okay, so let's make that precise. If we go back to the diffusion algorithm in network form, right, the way it works is I've got my WI, which contains the signals, and here a signal is my models, right, my model estimates at time I. And then I've got essentially an autoregressive process where my W at time I is a mixed version of the W at time I minus 1. And then that is driven by the gradient approximation vector, okay? So it's essentially an autoregressive process. The kind of difficulty is that, or kind of what makes this maybe a non-classical graph process is that what is driving my signal is nonlinear, depends nonlinearly on WI, right? And it's actually causing a drift. So it's not zero mean kind of noise that is driving me. It's actually the gradients that is driving each individual agents towards their local optimizers. Okay, but you can still think of this, or you can interpret this as now essentially a graph filter given by calligraphic A applied to a mixture of signal and a mixture of noise, okay? So the gradient is what's carrying the signal. It's what's carrying the information about the underlying optimal solutions, right? It's what's driving every individual agent towards their locally optimal models. So I would like to preserve that as much as possible if I'm looking for local optimality. And then you're also filtering the noise, okay? So I would like to filter as much of the noise as possible, right? So the question then becomes, how do I design a filter that preserves as much of the gradient signal as possible while killing as much of the noise as possible? Okay, and that will essentially correspond to a good prior. So in terms of this complication that I mentioned, which is that what's driving your signal, right, or what's driving your system is the gradient, which is a nonlinear function of WI. This is essentially a technical complication. So you can show, and this requires some proof, but you can very rigorously show that this process up here, which is driven by this nonlinear function, right, the gradient, you can approximate by a linear autoregressive process where now, this is a constant, and you're now just driven by a zero mean kind of noise process, okay? Where now the autoregressive process works on the error instead of the estimates themselves, okay? But fundamentally now, you can apply kind of these basic ideas from GSP, like the graph Fourier transform, to figure out how this kind of a system will evolve, right? And what it will ultimately converge to, and what the individual kind of frequency components of what you're left with are going to be, okay? So I'm skipping, a number of steps here, but hopefully the intuition is kind of coming through. Okay, so what is the kind of performance guarantee you then end up with? Okay, so to write this out, we're going to need to introduce the graph Fourier transform, which I'm guessing most of you have seen already, right? So as a shift operator, we've got the Laplacian here, and so we can, as long as it's symmetric, we can write down its eigendecomposition. So we use V lambda V transpose here. And then we can denote by V sub m, the mth eigenvector corresponding to the mth eigenvalue, okay, of this Laplacian. And then V sub m sub k is the kth entry of that eigenvector, okay? And then the quantity that we're interested in is what is essentially the MSD, right? So each individual local model is going to converge to the locally optimal solution of this maximum a posteriori problem that I formulated earlier. And then, this difference, we measure it in the mean square sense, and then we're going to average the performance across the entire network. Okay, and so the first insight is that this mean square deviation decomposes, okay, into individual frequency components, okay? So you can think of this error as consisting of a whole bunch of errors where each of this MSD of lambda m corresponds to the variation in the space spanned by the mth eigenvector, okay? And so this is kind of where the analysis or where the results diverge from a classical, let's say, consensus-based algorithm, because in a consensus-based algorithm, the idea is that I'm trying to implement essentially a perfect low-pass filter, and I'm trying to kill all but the leading eigenvector of the Laplacian. Whereas if you're interpreting this as a graph filter, which is softer, right? So you're not killing any variation in the signal, you're allowing for variation. Well, now when you study the performance, you have to figure out a way to quantify all of these MSDs. But it turns out that you can do it, and it has an interesting interpretation of essentially acting as a low-pass filter, okay, on the noise. So here, H is your Hessian of the kth objective. RS is the covariance of the kth objective. And then this term here, which is modulated by the eigenvector of the Laplacian, is essentially the transformation of the kth Hessian, right, into the space corresponding to this particular frequency. And then here you have the same thing applied to the covariance, okay? So what you have here is essentially the noise, and here you have the signal, right? So this is the inverse signal-to-noise ratio. But all of this is affected by your graph filter, right, which is given by lambda m, the graph frequency, and then eta, which is your tuning parameter, okay? So as you can now think of two special cases, let's say. If eta approaches 0, we end up at the non-cooperative setting, right? And there is no sort of filtering going on, and so you end up essentially, you let all the noise through and you let all of the signal through. Whereas if you let eta approach infinity, you end up killing all of the components essentially that correspond to any frequency other than 0, right? And so you're then back to consensus optimization. Okay, so visually what this means is we can interpret this kind of a decentralized algorithm as filtering the signal and filtering the noise, okay? So on the left-hand side, we have the signal, which is essentially the limiting point of the algorithm, transformed into the graph Fourier domain. And you can see that different choices of your eta, right? As you increase eta, this starts acting like more and more of a low-pass filter, okay? So what that means is if you start off with a signal which is, let's say, white, meaning there is no relationship between individual agents, you're going to end up with a signal that essentially has components across all graph frequencies. And so when you impose any sort of a regularization, it's going to bias you quite significantly. Okay, whereas if you start off with a signal, right, with a system of agents which are smooth or homogeneous across the graph, your signal is going to be essentially concentrated, have concentrated energy in the low frequency components of the graph Fourier transform. And so then any sort of filtering that you do on top is going to have less of an effect, okay? And the same thing is happening to the noise. So the noise is also being essentially affected through a low-pass filter. And so the ideal situation, right, for, let's say, a distributed learning algorithm is one where your signal is more or less a low-frequency signal, whereas the noise is white, okay? But fundamentally, right, we're back to this age-old problem of separating signal from noise and doing it in the frequency domain. Yeah, so, in practice, what this means is that this eta parameter is going to affect your bias and your variance, okay? So for very small choices of eta, you're going to be very similar to the non-cooperative solution. So you have no bias, but you have a high variance. And then as you increase eta, you're going to increase the bias, but reduce the variance, okay? And there is some sweet spot in the middle where you're going to have optimal solution. Okay, so then you might say, okay, well, what's the likelihood that the exact correct prior corresponds to the Laplacian of your communication graph, right? So this is a valid question to ask. But anyone who's worked on graph filters knows that you can implement, graphs using shift operators that have a very wide range of frequency responses, okay? So let's say for some reason you decide that this is the correct prior to use, right? Some R matrix. which comes from a Gauss-Markov random field. It's the precision matrix, let's say, of some particular distribution. Then, as long as R is a polynomial of the Laplacian, you can implement this very efficiently using essentially distributed graph filters. And so what we're showing here is, for different choices, things like the Laplacian, diffusion, random walk, band limited signals, right? So these are different kinds of functions of the Laplacian eigenvalues you can consider. You get different kind of behavior in terms of the MSD. And so what you can see is that, the Laplacian is not necessarily the right, the optimal prior to choose, because the set of parameters eta where you get very high improvement in performance is quite limited, okay? Whereas something like a band limited prior can give you better performance. Okay. So I'm quite conscious of time, so I will skip the second case study because this is actually more or less the same thing that I presented through the poster, okay? So if you have questions about this, you can come talk to me. But I want to talk about robustness a little bit, okay? So we were talking, a little bit about this idea that you have a heterogeneous set of agents where each agent is self-interested and each individual agent is looking to optimize its local objective while in some sense collaborating with others, okay? So you can interpret robustness in quite a similar way in the sense that when we have let's say, a malicious set of agents, you can decompose all of your agents N into a set of agents which are benign and a set of agents which are malicious, okay? And then benign agents are going to be denoted by this calligraphic NB, and their aim is to contribute to learning, right, in the classical way, let's say. So just to keep things simple, we're going to ask them to perform a consensus optimization problem. But we don't want to solve the consensus optimization problem over the set of all agents. We would only like to solve it over the set of agents which are non-malicious, right? So what you have here then is the average or the sum over the objective functions of the local agents, but only over the set of benign agents. And what makes this a difficult problem is that in general, you will not know who is malicious and who is benign, right? So how is this kind of approached? Of course, it's kind of a natural thing to consider, and so there's works along along this line. And typically, the way these problems are approached is by altering the aggregation. Okay, so classically, decentralized or distributed learning schemes work based on averaging, but we know that kind of linear averaging is quite susceptible to outliers, right? Because it essentially minimizes the least squares deviation amongst whatever you're receiving. And so any malicious agent is able to steer you quite far away from whatever the true average is. So kind of a reasonable thing to do is then to aggregate only in a robust way, okay? So I'm kind of quite generically denoting this by, the aggregation of the gradients over the set of all agents, right? But it's supposed to be a robust aggregator, okay? So a typical choice is to replace the average by the median, okay? So if I receive a whole bunch of gradients and I'm a fusion center, I'm able to just, instead of taking the average element-wise, take the median element-wise, and that's actually going to give me some sort of robustness already. Or in a decentralized setting, let's say if you're doing diffusion learning over a graph, you replace the averaging step, right, through an aggregation step, which is robust, but now everything happens just over a neighborhood, okay? And so the point is that if you use a full aggregation, okay, over a fully connected graph or using a fusion center, you're going to end up with a level of robustness which essentially matches the underlying the robustness of the underlying estimator, okay, which for something like the median corresponds to 50%, okay? So if you have a fully connected graph, as long as a majority of your neighbors are benign, you're going to end up learning the correct solution, despite the fact that there are some people who are trying to harm you. So a surprising insight, okay, is that if you choose your graph in the right way, you can actually do better than a fully connected graph, okay? And so this again goes to this kind of idea that exploiting the fact that there's an underlying graph can give me actually improved performance compared to a fully connected or to a centralized solution. So what's kind of the more formal objective here? Of course, if we know the state of the agents, the problem of designing a topology is quite trivial because we can just connect everyone who is benign. But in practice, we don't really have a exact knowledge of the state of an agent, but what we might have instead is an estimate of the risk, right? So what's the probability that an agent is malicious, or what's the probability that an agent is benign? And so, for example, if you have a sensor network, right, maybe you have function of the failure rate of your sensor over time, you have some idea of past behavior and so on. Okay, so the question is, can we design a sort of graph that takes into account the risk profile of the individual agents that is more robust than just putting everyone together? Okay, so then the question becomes, what do I need, right? What do I need? By the way, is it 5 minutes to talk or 5 minutes including questions? Okay, excellent. So what do I need for a topology to be robust? Okay, so if you look through any of these papers, you'll find that in order for a decentralized algorithm with the robust aggregator to be robust, let's say the robust aggregator can handle up to 50% maliciousness, what we need is, well, first of all, we need the graph, once we remove all of the malicious agents, to be connected. Okay? Because let's say in a perfect world, agents are omniscient, they know who is malicious, they cut all of the links to all of the malicious agents. If they then end up with a non-connected graph, that will just disrupt the flow of information, you will not be able to learn. Okay? But the second kind of condition that you have is that for any given agent, the majority of its neighbors will need to be benign. Okay? And that's because if I'm an agent and I'm receiving messages from, let's say, 60% malicious people, then I will not be able to filter all of them out, right? So I need, for every agent, the majority of its neighborhood to be benign, and then I need the remaining graph, once I remove all malicious agents, to be benign. Okay? So then you might say as a baseline, well, I would like to consider a fully connected graph. Okay? So if I connect everyone to everyone, this essentially maximizes the flow of information, so it might be reasonable to believe that this will give me a more robust solution, right? Well, in that case, of course, because everyone's connected to everyone, the connectivity condition is always satisfied. But the breakdown point being 50% means that as long as a majority of the agents are more likely than not malicious, as soon as I make the graph large enough, it will end up giving me, the system will break down. Okay? Whereas, if you end up strategically placing, right, if you're able to construct a topology that takes into account the risk profile of your agents, you're actually able to construct topologies which essentially have an inherent level of robustness, okay? And the way you do this is by very broadly decomposing your agents into a set of risky and a set of non-risky agents, and then constructing a topology which is more or less hierarchical, okay, which clusters safe agents together and clusters risky agents, kind of puts them along the edges. And so you can end up with a topology like this, right, where only 4 agents are benign, but this actually ends up being robust, okay? So the question is, based on the risk profiles, can you construct a topology which with high likelihood will end up giving you graphs like this, okay, given that you don't know a priori if an agent will end up being benign or malicious. So I will skip the details here, but rest assured you can come up with a systematic way of designing these graph topologies, and you can show that actually provably for large graphs, these topologies will be robust, even if the majority of agents ends up being malicious. Okay, so I will conclude here in the interest of time, and I'm happy, obviously, to follow up on any questions. But just to conclude, a typical paradigm in decentralized optimization is to avoid the network effects at all costs, right? So we're solving a consensus problem. We're looking for the kind of algorithm that minimizes the impact of the topology. But we saw actually that in 3 cases, there is a benefit, well, actually only in 2, because I didn't talk about one of them, but we saw that in 2 cases, there is a benefit to exploiting the underlying graph topology, okay? So it can give you an algorithm which performs better than a consensus algorithm. You can get algorithms which converge faster, so that's the part that I skipped, and you can get to algorithms which are more robust than their centralized counterparts. And kind of the key takeaway, hopefully for this audience, is that what we need to kind of study these kinds of systems are tools from graphical signal processing, and that's what's allowing us to move essentially beyond this consensus regime. Yeah, thank you.